Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and very good afternoon. Can you hear me?
Good afternoon.
Good afternoon, sir. Cancer.
Alright. Okay, let's go for the second class in the week number 2 for process control and dynamics. Just before we begin, anybody would like to share me what has been learned in the last Monday? Anybody?
Overall balance.
What is mean by overall mass balance? What is the function to derive overall mass balance? Aaron Raj? Aaron Raj, are you there? Oh, it's not there. Irene Siu.
Yes, doctor.
What is the function of deriving overall mass balance?
The formula.
Yeah, so the formula is for what?
Mass accumulation equal to mass in minus mass out.
Okay, thank you, Irene, for your response. So in this case, when we try to derive overall mass balance, the main objective is to observe how the mass accumulated in the system. Because here you have the flow in and flow out. When you have a flow in and flow out from the system, meaning that the volume inside, the mass and the volume inside of the unit operation will be changed. So it is essential for us to derive overall mass balance in order to determine how the mass change occur in the system. Is it increase? Is it decrease? So that can be determined by using the overall mass balance. The same goes with the component balance. When the component is reflecting to the specific component involved in the unit operation. Still, it's accounting the mass only. It is specifically accounting the component in that unit operation. So that has been covered in our last class. So today we try to complete the mass balance again. Just to recall, we use the blending system for our case study, where in this case you have 2 inputs and 1 output. So far we already covered the conservation of total mass, where we get the final overall mass balance density multiplied by dV over dt equal to F1 plus F2 minus F3. So that accounting your mass balance. And then for the conservation of component, this case study involved 2 components, component A and component B, where the unit involved for the component is by mass fraction. So we account the mass change of component A, and in the end, we get the following component A balance. So since in this case is involved 2 components, there are 2 ways to obtain the component B. The first approach is to derive it back like what you did for the component A balance. So you will get the expression or mathematical model for component B. Or others, we can use the relationship of the mass fraction where the XA plus XB equal to 1. So by having this one, then we can obtain how the mass of A and mass of B is changed against time. So this has been completed. So now we want to concentrate on the conservation of energy. So by looking at the given equation, the rate of energy accumulation is equal to rate of energy in by convection minus rate of energy out by convection. And it also need to add with some of the heat addition from the surrounding plus the net rate of work. So like I mentioned it before, normally for our case, the rate of work normally is not considered. So we can neglect the net rate of work. So this one equivalent to 0. We don't concentrate more on the shaft work and so on. We just focusing on the net rate of heat addition, where heat addition to the system from the surrounding usually coming from the use of heater or coil. So heater, or sometimes we use it as a coil to supply the heat into the system. Why we need to supply the heat? Sometimes we need to achieve specific temperature inside the unit operation. In the chemical industry, normally the inlet is under atmospheric temperature or ambient temperature, 25 degrees C up to 28 degrees C. It does not change much. So sometimes when we want to blend the system, we want to mix the component, it's better to operate at higher temperature, more than ambient temperature. Why we heat it? Because it's much more easier to mix up or to mix the component in order to achieve uniform composition at higher temperature. This can be observed if you try to prepare the instant coffee or sometime maybe you want to prepare simple beverage using either instant cocoa or so on. Okay, hold on for a minute. Okay, normally when we want to prepare our beverage using the instant coffee or instant cocoa, we use hot water as our medium. We put the instant coffee, we put the sugar or creamer, and then we put the hot water inside the mug, and then you stir. So it's much more easy for the solution to dissolve until you get the uniform composition. So that's why for this case, the blending system, we include the heater to heat it up, the solution inside the unit operation. In the end, you can get the uniform composition, and as a consequence, the temperature inside will also be changed. That's why you need energy balance to account how the temperature is changing against time inside the unit operation. So based on this, we still use the same case study where right now the rate of energy accumulation. So we start with the derivative. D E over dt. So this dE over dt represent the rate of energy accumulation. We start the E stand for the energy. So this is the rate of energy accumulation. And then equal to rate of energy in by convection. So we put E dot in minus E dot out plus Q, where the Q here coming from the heater. As I mentioned before, the work is not included, so you don't have any W. So you have only one term on the left hand side and the three term on the right hand side. The left term, rate of energy accumulation, normally in the form of the differential equation, because we want to observe the change of energy against time. So when the time is moving, so the easy way to represent it by using the derivative. So in this case, based on the thermodynamic, the energy normally consists of the three type of form, where energy can be equivalent with the U plus KE plus PE, where the U itself is represent the internal energy. Internal energy. The energy contained in the substance, in the unit operation itself. And the KE is represent for the kinetic energy. And lastly, the PE represent the potential energy. So this is the form for the energy. If we recall, by first law of thermodynamics, it said that the energy cannot be created, cannot be generated. It can be transferred from one form to another form. So what is the form is based on the internal kinetic potential. However, in the process control, normally we assume the unit operation is installed on the ground. It does not moving. It becomes stationary. And since it is stationary and it does not influence by height, the difference of the height, then normally the kinetic and the potential will be neglected. So the KE here is neglected for our case. It is a common practice to assume both are neglected because the unit operation installed on the ground, it is not moving, hence it is stationary, and also it does not influence by any height. So we just focus on the energy change based on the internal energy. So in this case, the E equal to U, where according to the thermodynamic, the internal energy can be represented by the change of enthalpy. So normally here we use the H plus delta PV, the one that we use or apply in the thermodynamics, where the internal energy represented by the enthalpy H plus the pressure difference multiplied with the volume or the specific volume. Again, in the blending system, normally we operate under ambient pressure, atmospheric pressure. So the pressure is not going to change. So when the pressure is not going to change, then we further reduce the equation. So that the delta PV becomes 0. That leaves us the energy is in the form of the enthalpy. So in here, the enthalpy can be expanded into the M multiplied with the H. So where the M here is stand for the mass. And the H here is the specific enthalpy. It's a different. Capital letter of H represent the enthalpy and small letter of H represent the specific enthalpy. It's referring to the enthalpy, only the unit is different. For example, in this case, specific enthalpy has the unit of kilojoule over kilogram. So mass of kilogram. So when you try multiply it, you get the enthalpy in the unit of kilojoule. So based on the specific enthalpy here, it can be further extended. It can be further extended in the form of the heat capacity, mCp delta T, like what you learn in the energy balance, material energy balance subject. So there's a lot of the expansion, how we from one symbol we can further expand it. So based on this, you have the M for the mass, the Cp for the heat capacity, and delta T. Normally we assume it T minus T reference to reflect the change on the temperature. Of course, in the thermodynamic, normally the reference temperature we normally use is 25 degrees C as a standard temperature based on the STP, standard temperature and pressure, where the P is 1 atm, temperature at 25 degrees C or ambient temperature. So if we try to include 25 degrees, then this equation still getting complicated. So for the process control subject, we further neglect the T reference, or sometimes we use not 25 degrees C, but we use 0 degrees C, just to eliminate the reference temperature variable. So when we assume the reference temperature equal to 0, then automatically T reference will be neglected, become 0. So that reduce the equation into E M Cp T. So we just have 3 variables inside compared to 4. So this is sometimes we need to do the simplification for the sake of the solving our mathematical model. So here mCpt represent the energy, and sometimes we can further expand it. Rho V Cpt, where we assume the mass equal to density multiplied by volume. So you get the E equal to rho V Cpt. So now we have the final form of your energy in the form of the 4 variable: density multiplied by volume multiplied by heat capacity multiplied by temperature. So what is the function of obtaining this form? Of course, because here we want to do the derivation. So this 4 variable in the end will be substituted into our differential equation. Remember that we have the dE over dt equal to E in minus E out plus Q. So we will substitute the obtained term inside the E. When we try to substitute it, your equation now become d rho v Cp T over dt equal to E in minus E out plus Q. So here the term E for energy has been replaced with the rho V Cp T. Any question so far?
Nak tanya boleh?
Boleh.
Yang T reference tadi, kenapa dia equal to 0
Okay. Why we assume the T reference equal to 0? Because in this case, we want to simplify our term. Imagine that if we use, for example, in this case, E equal to MCP T minus T ref. So we try to substitute inside the dE over dt. This one, we try to substitute it here. So this equation become the MCP T minus T ref over dt. So when we have like this, it's getting complicated to do the derivation. So for simplification, we assume T reference equal to 0. That is why we assume as a 0 because we want to eliminate the term of T reference. So when we try to eliminate it, your equation become more simpler than before. Any other question? Okay, if there is no further question, then I continue with the lecture. So now we have the d rho VCPT over dt, the left-hand side. We focus on this first part first, the highlighted one. So on the numerator, we have 4 variables: density, volume, Cp, and T. So among these 4 variables, we can say that the density and the heat capacity is constant. This one normally is a constant variable. For example, the density of water. The density water we use is 1000 kilogram per meter cube. Tomorrow still, we use the same value of our density of water, 1000. So it's not going to change. The same goes with the heat capacity, where the heat capacity of water is around 4.14. So this value also is a constant. So when we have a constant value, then we can take it out from our term. Where now the equation, you have the rho Cp d v t over dt equal to E in minus E out plus Q. So when we have the two terms inside the differential equation, then it's much more easier to expand it. So we can apply the UV substitution according to the mathematical derivation. So this become V dt over dt plus T over dV over dt equal to E in minus E out plus Q. So we have the expansion of differential equation from single term dVt over dt, it become V dt over dt plus T dV over dt. So based on this, we can say that dt over dt here is for the temperature change. And the dV over dt here is for the volume change. So we have the term, the function of the term accordingly. In this case, normally the volume change can be substituted based on the derived overall mass balance. If we take a look further in the previous lecture, we have this one. Rho dVdt equal to F1 plus F2 minus F3. So in this case, normally we can substitute the equation. So we have the rho dVdt equal to F1 plus F2 minus F3. So this from overall mass balance can be substituted into the given equation. So you have the dVdt inside. From mass balance, rho dVdt equal to F1 plus F2 minus F3. So we can further rearrange it. dVdt equal to F1 plus F2 minus F3 divided by density. So you have the similar term which you can substitute the following term inside the equation. So when we try to substitute it, then your equation become rho Cp V dt over dt plus T F1 plus F2 minus F3 divided by rho. We close the bracket. So this is the left-hand side of the equation. So here, if we try to complete it, equal to E dot in minus E dot out plus Q. So right now, based on this, we already complete the left-hand side of our equation. All has been substituted. The next step may involve the expansion. We can try to expand our equation. So for the left-hand side, LHS. So here the LHS stands for the left-hand side of the equation. So I focus on the left-hand side first. Rho Cp V dt over dt plus rho Cp T. So since here you have the density and the equation for the second term, you also have the density, then it can be eliminated. So you have the Cpt F1 plus F2 minus F3. So on the second term of the left-hand side of the equation, you no longer have the density because it has been cancelled out. So this equation can be further expanded. Rho Cp V dt over dt plus Cp Tf1 plus Cp Tf2 minus Cp Tf3. So this is the complete version of the expansion of term in the left-hand side of the equation. Okay so far? I think now, yeah.
Yang left hand side, yang bawah tu dikira sekali left hand side ke macam mana?
Yeah, all of it is in the left-hand side.
Okay.
So I think now you notice that why this subject is so difficult. Because it involves the derivation. Imagine that if you wrongly derive the equation, then ultimately it will affecting all other equation. So that's why you need to focus, you need to try yourself digest it carefully how this equation has been derived. So now here, based on this, is just for the left hand side. This one is only the left hand side of the equation. So we are focusing on the right hand side now. So for the right hand side, based on this equation, you can see equal to E in, E out plus Q. So we have the E in minus E out plus Q. So based on our diagram, okay, the blending system here, you have two inlet, the first inlet and the second inlet. So we need to add both inlet in the form of the energy. So normally based on this, we consider the flow coming into the system. So we have the flow F1 coming. Of course, this flow will carry some energy. And then here, normally this one will multiply with the Cp and T to account the enthalpy carried by this flow. So we have the F1 Cp T. If you're not sure, then we take a look on the unit. F1 here, based on the given unit, is kilogram over minute. Cp, kilojoule over kilogram degree C or Kelvin. And T here will be degree C. So if you try to cancel it out, degree C, kilogram, you got kilojoule over minute. So the kilojoule over minute represent the rate of energy. So meaning that you can check either the variable is correctly formed or not. Because based on this, if we take a look again, here the density, kilogram over meter cube, multiply with the kilojoule, kilogram, degree C, multiply with the volume, multiply with the dt over dt is the degree C over minute. dt, temperature. The small letter of T is minute, is the time. So when you cancel the unit, kilogram, degree C, meter cube, you get kilojoule over minute. So here you can verify either you have the unit consistency or not. It's like that. You don't need to memorize it, but you need to have the concept of it. As long as you understand it, then you can form the accurate term for this part. So in this case, we back to the right hand side. We already have F1, Cp, and T. This one is supposed to be T1 to represent the inlet number 1. And then you have the second inlet. So the second inlet, you need to add F2, Cp, T2. So F1 Cp T1 and the F2 Cp T2 represent the energy coming into the unit operation. So we complete the E dot in. Now we focus on the E out, where you have the exit flow rate. Still, it follow the same term, F3 Cp T3. So you can take a look on the E in and E out. You have the same symbol, only different numbering. It makes sense because here the energy is carried by the flow rate. So of course you need to have the same term. Maybe the different in the form of the numbering for label. 1 and 2 represent the inlet and this number 3 represent for the outlet. So we have the E in minus E out plus Q. So Q stand alone. You don't need to expand it. For our case, in this subject, the Q, normally we give the value. So you don't need to substitute with the other expression. So we just leave as it is, the Q. So here we already complete the right hand side of the equation. So every term has been identified as the final variable. So the next step is to combine it all. We have the left hand side, and then we want to combine it with the right hand side. So this is the left, this is the right hand side. Any questions so far?
Doktor,
Ya.
yang CP dekat F1, F2 dan F3, CP dia tak label CP1, CP2, CP3 ke doktor?
Okay, thank you. Very good question. Alright. In this case, of course, you can do it like that to make it uniform, standardization, to make it standard. For E in, E out, if you want to label it CP1, CP2, CP3, it is okay, no problem. Only in this case, normally, if we put it labeling CP1, CP2, CP3, we can include one assumption where here we can assume CP equal to CP1 equal to CP2 equal to CP3 equal to constant. So why we have this kind of assumption? Because right now normally the heat capacity does not change much from one component to another component. So we assume the effect of heat capacity is minimal. So we can use this following assumption. CP equal to CP1 equal to CP2 equal to CP3. So for constant variable like this, CP, heat capacity or the density, we can have this kind of assumption where we assume the value of the heat capacity and the density for each stream are equivalent. So right now, we want to rearrange our equations. So we have the rho CPV dt over dt plus CP TF1 plus CP TF2. And then CP TF3 minus CP TF3 equal to F1 CP1 T1 and then F2 CP2 T2 minus F3 CP3 T3 plus Q. Okay. So this is the complete version of the energy balance equation. So here, if we can see based on the current arrangement, you have the CP, you have the CP1, CP2, CP3. So this is the importance of the following assumption. If we assume it's equivalent, CP equal to CP1 equal to CP2 equal to CP3 equal to constant, then we no longer have the one here, the labeling here. So this means when we don't have the numbering of the CP, your equation become much more simpler. Because here the objective is to obtain the model. So the model sometimes we want to have the understandable or the relevant equation only. We don't want the equation to get so complicated. When you have complicated equation, then it's much more harder to solve it. So this is the important why we assume the CP for each stream are equivalent. In this way, you can eliminate, or we can have the equivalency of the heat capacity on the left and the right hand side of the equation. So we have the T1, T2, and T3. So in this case, if we take a look, the T1 is located at here. This is our T1. This is our T2. And this one is our T, or sometimes in the numbering, I put T3. So normally, the temperature T is coming from the inside the unit operation. So when it's coming inside, in the end, it will eventually exiting the system through the stream number 3. So for this part, normally the T itself is equal with the T3. Because we assume this one is a perfect mixing. You have the stirrer here. Then you have the well-mixed solution. Or sometimes we call it perfect mixing. So when you have the perfect mixing, not only you have the uniform composition, but the temperature inside is perfectly balanced. And in the end, the temperature inside will exiting the system through stream number 3. So that's why we can assume the T equal to T3. So that makes that in here, the T3 over here is equivalent with the T. So T equal to T3. So what is the implication of it? When we have the T equal to T3, you can see that this term F3CP3 on the right hand side of the equation, and then you can see the CPT F3 over here on the left hand side is the same variable. So when you have the same variable, you rearrange it, you can cancel the equation, the term. So this equation can be cancelled. It's like that. And then the rest of it, we can further rearrange it. So your equation, if we rearrange, rho Cp V dt over dt equal to F1 Cp T1 minus T plus F2 Cp T2 minus T plus Q. So this is the results or the outcome from your energy balance equation. How I get this? Here, for example, you have the CPT F1 here. You have the F1 CPT1 here. So I bring this term CPT F1 to the right hand side and I rearrange it. So you get the final equation like that in the bracket.
Sir,
Yeah.
do we need to show all the derivation in exam, isn't it?
Okay. This is depends on the question actually. If the question asks you to derive, then you need to show it in detail.
All right. So thank you.
So let's say, for example, the question asks you derive energy balance for the given system. So let's say sometime maybe some of you is too familiar with the equation, then they just obtain or show the final equation. So let's say the mark is 10. If you don't do detailed derivation, you get the final answer is correct, then you will get the full mark for it. Let's say your final equation is wrong. Then this is where the detail of the derivation must be shown. At least you get some mark for it. So that is the way how to include the derivation or not. In some cases, the derivation or the mathematical model is given. So you don't need to do the derivation. How to know when to derive? Normally, it is depend on the question. So we specifically said derive the overall mass balance. So of course you need to show the detail. The term is derive. Any other question?
Doktor,
Yes.
dalam buku dia pakai CPTW1. Apa beza dia dengan F1?
Okay. Thank you. All right. In this case, it will depends on the version. Alright, in your textbook, normally we refer the flow rate. Flow rate has different symbol. Sometimes it refer to the F, it refer to the W, it refer to the Q. Oh, sorry, not small letter, just a small letter Q. So what is the difference? Okay, in this case, you need to be very careful. You need to check what is the unit used for the given symbol. In the textbook, they use the W, and then if you take a look closely, the unit should be kilogram over minute, or sometime maybe kilogram over hour. For this part, the flow rate, if you take a look, the F here in this question is given in the form of the kilogram over minute. In some cases, F or Q can be in the form of the meter cube over minute. So the flow rate sometimes can be in the form of the mass flow rate. Mass flow rate, you have the kilogram over minute. Or sometimes maybe other unit, pound over hour, for example. As long as the dimension is mass over minute, that is mass over time, that is acceptable for the mass flow rate. And another form is the volumetric flow rate. So volumetric flow rate normally based on the volume over time. Let's say for the meter cube over minute, or sometimes liter per hour. So this is the unit used for the volumetric. So based on the textbook, it use W. The W over there is stand for the mass flow rate. And for my exercise, I use F. Also the mass flow rate. So it's the same thing, only the different symbol. What you need to aware is what is the unit given. The symbol is okay. Sometimes the unit sometimes is different. Either it's mass or volumetric.
Doctor, one doubt.
Yeah.
Doctor, why did not we expanded for Q? Because we can write Q as CMCP delta T. So it would be easy to cancel CP, right?
Okay, thank you for your question. All right, in this case, where is the diagram? All right. So here the Q coming from the heater. So here, why don't we use QMCP delta T over there? The problem here, this Q is by convection. The convection, if we refer to the notes, in this case, the rate of energy by convection, and this one is heat addition to the system from the surrounding. So MCP delta T in this case, normally used for the case of convection. But for our Q here, it's not by convection, it's supplied from the coil. So in the coil, we have a different term for the Q. We cannot use the MCP delta T. We use QUA delta T. So you have the overall heat transfer coefficient, U, and the A, the area of heat transfer. So that's why we cannot simply use the MCP delta T for replacing the Q. It's just for the flow rate by convection. We note that the flow rate here is mixing inside, but the Q here does not mix with the solution inside. So we cannot use the MCP delta T. If we want to substitute with the other term, we need to use UA delta T. However, in the PCD, in this subject, we don't explore further by using UA delta T. We just give directly the value of Q for simplification. Okay, any other question?
Doctor.
Yeah.
So for the CP, we know that every substance has different CP. So for the question, will the CP will be given, or we need to calculate if the substance inside the flow stream is more than one?
Okay. Thank you very much for your question. All right. It is true. Every component has a different value of heat capacity. Let's say you have 3 components inside. So these 3 components will have different CP. However, in the derivation, you can see that we assume all the CP has the constant value. We assume all of the component has one value only. Why we do that? Because to simplify. So in this case, normally, the CP will be given directly. You don't need to find the CP for each component. We just give the average value of CP for each component. So you don't need to find in the literature or what, because that is not objective for this subject to find the CP. The CP itself has been covered in the thermodynamic. So here we just simply use the value of given CP. So no matter how many components involved, we just give the average value. Then you just directly use it. And one more thing, this assumption CP equal to CP1 equal to CP2 equal to CP3 is valid for this subject. So you feel free to use it. You don't need to find individual heat capacity for component. Any other question? If not, then we take a break for a while. So we continue 5 minutes later. Okay, let's continue our class for the second part of this timetable. One more thing, I also would like to welcome to our friends from India who participate as the part of mobility program in this case. Astana, right?
Yes, sir.
How are you?
I'm good, sir.
Yeah, maybe you can introduce yourself, where you come from and so on.
I think I already made an introduction on the first class, sir.
Yeah, really? Okay, all right. So just for your information, for all of you, since we have our friend from India, so please speak English. If you want to ask the question, speak in English so our friend can understand that. If I'm speaking Malay language, please correct me. Please notify me so everybody will understand what has been discussed. So here we continue. All right. Based on this, we already complete the balance of the overall component and the energy balance. So let me summarize a little bit. Overall mass balance. So we have the rho dVdt equal to F1 plus F2 minus F3. And then we have the component balance. Component A balance. So the component A balance is this one. Okay. So we have three balance: the energy, the overall mass, and the component. So this represent the common balance that need to be developed in our study. All right. Oops. Let me rearrange a little bit. Okay. So based on this, we can see on the left-hand side of the equation is consists of the differential equation, the d over dt. So this represent the change of the volume of the composition and the temperature. In some cases, sometimes the overall mass balance, rho dVdt, can be further expand to reflect the level, where we assume the V equal to A multiplied by H, where A is stand for the cross-sectional area. Since this case study involved the blending system, so you have the sectional area for the system, and the H is the level So based on the given study, the H normally represent this part. H level. Where here the A is this. This is your A, the cross-sectional area for the tank. So normally, what is the formula for the area? And before we come to that question, what is the common shape used for the tank?
Cylinder.
Why it is cylinder? What? Why?
Usually the tank or the CSTR is cylinder.
Why not square?
Because curved surface allow more mixing.
Yes, correctly. When you have the curve, it's much more easier to have the mixing compared to the square shape. That's why in almost all cases in the chemical industry, they use the cylinder shape other than the square. Squares normally is just only for the storage tank. When you don't need to have the mixing, you just store the liquid, then you can put the square if necessary. But if it's involved the mixing, in order to have the proper mixing of your liquid, so we use the cylinder, where the area for the cylinder normally is represented by the pi multiplied by the radius r square, pi r square or pi d square over 4. So this is the standard formula for the area used for cylinder. Either you can use the radius or you use the diameter. Both are acceptable. So in this case, the volume can be represented by the area multiplied by the H. H is the height of your liquid inside the tank. Or sometimes we call it as a level. Level or height. Height of your liquid. So when you have the V equal to AH, then this equation can be further extended. dAH over dt equal to F1 plus F2 minus F3. Then this can be further expand to become AdH over dt plus H dA over dt equal to F1 plus F2 minus F3. So based on the expansion, you have two terms, A dH over dt plus H dA over dt. The first term, H over dt, is reflect the change of your level against time. Change of level. And here, the dA over dt, change of area. Based on the definition, dA, change of area against time. So for this part, if we put into perspective, normally we use the same shape. For our unit operation, the area does not change against time. If we operate the blending tank for 24 hours, still we use the same unit operation, thus the same shape. This indicates that the area will not change against time. So the dA over dt over here will be neglected because the value of your area will not be changed. It does not make sense how the area can be changed. You will use the fixed shape all the time. So based on this, you get the rho A dH dt equal to F1 plus F2 minus F3. So this is your final in the form of the level against time. So here either you can finish dv over dt or you can further expand for dh over dt. Both are acceptable. It depends on the question. Sometimes they ask you to determine the level. So when the question asks you to determine the level, this means you need to obtain the dH over dt, where the H stands for the level or height of your liquid solution. So for this part, if we take a look, you have three different equations obtained from the conservation, mass and energy principle in the form of the dH over dt, dXA over dt, and dt over dt. In the form of the process control and dynamic, the basis of it, normally the variable inside the differential equation is also considered as your control variable. Again, I repeat, the variable located at the differential equation, such as in this case H, XA, and T, is normally considered as your control variable. Control variable, the variable that we need to control. So this is sometimes we call it as a CV, control variable. Why we need to control the level, the composition and temperature? All right. If we take a look on this case, on the diagram, here normally the tank has its capacity, minimum and maximum capacity. So what happens if we put too many liquid? The flow rate is too high and the exit flow rate is too low. So this means if your inlet is too high, is higher than the flow rate exiting the system, theoretically the level will keep increasing. So what happens is it is keep increasing against time. In the end, it will overspill. The liquid exceed the maximum level, the maximum capacity, and become overspill. And another way, if the exit flow rate is too large compared to the inlet, then what happens to the liquid level is it will keep decreasing. When it keep decreasing against time, eventually, maybe your tank become empty. So this is why we need to control the level, because we want to make sure our level is keep maintaining at the certain point, at the certain value. So this is also the important why you need to derive the overall mass balance, because from the overall mass balance, it will account the accumulation of mass or volume inside the tank. So for this case, the CV for maintaining the level will be your H, the level. And then for the XA, the composition, why we need to control the composition? Of course, every unit operation has its own objective. Normally for the mixing tank, we need to obtain desired composition of component. That's why we mix the component. So in the end, we will obtain the desired or we achieve the target composition. So XA is also considered as the control variable. And of course, the temperature. The temperature, because here we put the heater. If we put the heat continuously into the system, maybe at certain point, some of your liquid will be evaporated. Or maybe In some cases, if the heat is too low, the temperature is not going to change much. Maybe you want to make sure the mixing process conducted at temperature of 70 degrees C, 70 degrees Celsius. If your heat is too low, maybe it's around, you achieve around 50 degrees C. So you will not get the uniform composition accurately. You will take a longer time to make sure you get the uniform composition. So that is the reason why in this case the temperature needs to be controlled. So based on this, you have the H, XA, T. It's easy to determine the control variable because it's normally located at the differential equation term. So dH dt, you have H as your control variable. dXA dt, X as your composition. Temperature in the dt. So this is the normal control variable used in the chemical industry. In addition to that, we also have the pressure. Pressure and sometimes maybe flow as our CV. For our subject, normally we assume all of the operation is conducted at atmospheric. When it is atmospheric, you don't need to control the pressure. It is natural to have the atmospheric pressure at this condition. So that's why we no longer, in this equation, we no longer consider the pressure control for this case study. And for the flow, because it's only the single unit pressure. If we control the level, we don't need the flow. The flow, when you want to merge or you want to split the piping, then you will include the flow control. So for this part, only 3 control variables involved, which is the level, the composition, and the temperature. So any questions so far?
Doctor,
Yeah?
what about XB?
All right. Thank you. So now, do we need to control the SB? In this case, we need to be realistic. All right. Since the XA here is represent the mass fraction. And for our case, we know that XA plus XB become 1. Because you only deal with 2 components, SA and SB. Of course, when you add up both components, it will resulting into 1 as your mass fraction. So the question here, do we need to control SB? Now, in this case, we have the XA. So when we control the SA, automatically it will contribute or indirectly control the XB, where SB equal to 1 minus SA. So we control SA, automatically you get the SB. So the answer for this question is we don't need to control the SB because it has been directly controlled when we put the SA as our control variable. So the next question, what if we control SA and SB? What happened? We control both. We put our controller for maintaining the SA, we maintain the SB. What happened? Anybody?
Interval reading because both will be taken and listened, so the reading will be overlap.
Yeah. Okay, thank you. So when we employ both controller SA and SB, what happened? normally you will have what we call it conflict condition of controller. Conflict condition. When you have the conflict condition, that means it will be cause the violation of your control condition. So normally in practice, we will not enforce two controller for the SA and SB because in the end you will get the violation. Your controller become conflict. So when your controller become conflict, it will lead to the imbalance. Maybe in some cases you want to control SA at 0.7. So because here let's say if we try to imagine SA, we want to control at 0.7, automatically you have SB at 0.3. Let's say in this case, you want to control SA 0.7, SB 0.6. Then we can see if we add up 0.7, 0.6, 1.3 is violating the rules. That's why process understanding is very important. We cannot simply put two controller at once for composition. We need to check the basic rule. If we enforce like this, then both will not achieve the desired condition. That is the consequence of having two controller for SA and SB. So in this case, if we control the SA, then we don't need to control the SB. Or maybe you want to control the SB, then you don't need to control the SA. Just one of the choice.
So how about the that you say for the level and for the flow? Because usually we see in the PFD or basic, we see the valve always control the flow, but not the level. So how we want to manage that?
Okay, thank you. All right. Okay, in this case, can you see my screen now?
I can see
It's blank, right?
No, not blank.
Not
The
blank.
form.
Okay, wait. Okay. All right. So, in this case, when we want to control the flow, when we want to control the level. Okay, in my case, right now, is only involve one unit operation, which is this one, the blending tank. So when you have one unit operation, the scope is narrow. You just want to make sure the level will not exceed the capacity or will not violate the minimum capacity. So in this case, only level control is necessary. Flow control is not needed. All right. So when the flow control must be used? All right. If we look at the process flow diagram, in the process flow diagram, normally it will involve multiple unit operation. You have like this, you have like this. Okay, this is just for illustration. All right. So when you have multiple unit operation, then we need to ensure we also control the flow. We need to imagine, normally the location of the tank is not near, it's not adjacent. You put the one tank here and then beside this tank you put another tank. Sometimes it's not that the case. The location of every unit operation sometimes is a little bit far. more than 5 meter or 10 meter because of the safety purpose. So in order to ensure you have the correct flow, then normally for the multiple unit operation, you will involve the flow control. For the unit operation, you will have the level control. It's like that. The flow control objective is to make sure you have continuous or consistent flow rate going into the next unit operation. So it will regulate the required flow. So this is where you need to implement the flow control. But for our case, for today, I just involve the one unit operation. So it's just necessary to control the level because I assume only single. There is no other unit operation. So for the next task is involve the assignment of piping and instrumentation diagram, PNID. In this PNID, it will involve the process flow diagram where you will deal with the multiple unit operation. In that way, we will consider the flow control for our case.
Dr. Mike.
Tak, saya baru tulis, saya tak cakap lagi. Alright. Okay, now in this case, we already identified what is our CV control variable. So here we want to develop the configuration control. Configuration control means how we can control the given variable. So we have the H, we have the XA, we have the T as our control variable. So we want to find what is the suitable manipulated variable. Manipulated variable means the variable that we can adjust in order to make sure we obtain the desired value of our control variable. And the disturbance, what is the variable that will affecting our process from obtaining the value of control variable. So you have the manipulated and disturbance. So if we take a look on the case here, for the overall mass balance, we have rho A dH over dt, and then equal to F1 plus F2 minus F3. So in this case, we have the rho density, we have the A, H, F1, F2, F3 as our variable. The time will not consider as variable because it's a trajectory. T is the time for the trajectory, so we cannot control the time. We just let the time continue. So among these 6 variables, we know that the H is our control variable. So H is our CV. And then you have the density and the area. The density and the area normally is constant variable. So when it is constant, you cannot do anything about it. You cannot adjust the value. So this one is out of the question because you cannot do anything, then it will not affecting much. So this is considered the constant variable. And this leave you the F1, F2, and F3. F1, F2, and F3. So for this part, we want to select what is our control variable, manipulated variable, and disturbance variable. So now our control variable is the level. So which variable should be selected as our manipulated? Note that manipulated variable means the variable that we can use to help or to assist our control variable H maintain at its value.
F3.
Why F3?
Because you control, you can control the height of the outlet. But you can stop or make it open to lower the height.
Alright. Okay. So in this case, how to decide based on the variable? We don't see the data yet. We just analyze in terms of the variable F1, F2, F3. We know that the F1 and the F2 is our inlet and F3 is our outlet. So basically, since we want to maintain the level, it will be good if we observe how the flow coming into the system. So in this case, let the inlet coming in and see the level, how it look like. Is it reach our value or not? Then we decide. So how to decide is based on the outlet valve or outlet flow rate. So in this case, normally for the level, we will use outlet flow rate as our manipulated variable. Why? Because if we try to do the inlet, here you have to inlet. And then this inlet will affecting first the liquid. So it's better to observe how the inlet influence your level before you adjust the exit flow rate. It's much more easier compared to selecting the inlet as your manipulated variable. So that is the explanation why the exit flow rate is most suitable to be used as your manipulated variable. So here, this F3 is become your MV, manipulated variable. So that means we want to control the level by adjusting the F3 value. If the level is too high, exceeding the limit, then we increase the F3 flow rate. If the level is too low, then maybe we decrease or we close for a while our F3 flow rate. That is how you can adjust your level accordingly. So we have the CV, H, MV, F3, and the remaining F1 and the F2 will become your disturbance variable. So based on this table, H is your CV, MV is your F3, and the disturbance will be F1 and F2. Normally, for this case, for the control loop or control configuration, If we have one CV, it must be paired with the one MV. One control variable must be paired with the one manipulated variable. That is the rule. That is why we call it as a single loop. One CV, one MV. But we can have more than one DV. Disturbance variable is okay because sometimes the disturbance is just affecting the process. It can be more than one. But for this case, since for the pairing, we control the level, it must be paired with only one manipulated. That is the rule. One CV, one MV. But you can have more than one disturbance variable. So that is the explanation on selecting CV, DV, and MV. Next, I will explain about the control configuration. So based on this, our CV is H, our MV is F3. So F3 is located over there. So in order to draw the configuration, so this is your level. So you have the straight line, and then you have the LT, where L is for level. T, in this case, transmitter. LT, level transmitter. The function of level transmitter is to measure what is the current value of your level. What is the current height of your liquid solution in the tank. So that is the function of the LT, level transmitter. And then, based on the LT, you have this dashed line. It's connected with the LC. C for the controller. C. So LC, level controller. LT, level transmitter. So once level transmitter measure the level, then it will compare with the reference value, or what we call it set point value, the value that we want to achieve. Let's say you want to achieve the level at 5 meter. Current level 6 meter. So you exceed by 1 meter. So the controller will adjust, calculate how many flow rate need to be adjusted. So that is the function of the controller. And then in this case, once you have the LC, you need to include the valve. So this is your valve. So it will connected to LC to the valve. You have the line like this. So this is what we call it configuration control loop. Control loop for level. Based on this configuration, you can see 3 different lines. You have solid line, you have dash line, you have this line, kind of line. The solid line represents the piping line. The dash line here represents the electrical line. And lastly, the line with this symbol is what we call it pneumatic line. So this is the general labeling for line used in the piping and instrumentation diagram. where the piping line here, the solid line, where you include some of the line inside the tank to observe what is the current level. So normally level transmitter is based on the electrical device, and the controller also electrical device. That's why you have this dash line between LT and the LC, transmitter and the controller, because it involves the electrical device. And then for the LC to the valve, it become pneumatic line. In the pneumatic, you will change the symbol, the signal from electrical to the flow rate. So pneumatic will change the signal. Controller will calculate how many flow rate and send the information in the electrical line. Then pneumatic function, it interpret the electrical value into the valve opening. How much the valve needs to be turned in order to produce the desired flow rate. The valve itself, if we imagine, it's like a head of pipe. It's a pipe, water pipe. So how many it's turned represent the flow rate. So that's why you have the pneumatic line. So this is the configuration control loop for level. If we want to apply into another variable, we just simply change to the other related variable. For example, let's say you want to control the temperature, you use TT, and then you use TC. TT stands for the temperature transmitter. TC, temperature controller. But the arrangement is the same. It's like that. If you want to control the composition, you can put XT, XC. Or sometimes they use CT or CC. Composition transmitter, composition controller. Depends. Both are acceptable. Either you use X or C. The most important thing, the second alphabet should be transmitter and the controller. So based on this, you take a look on the equation overall mass balance. You list all of the equation. If the variable is constant, you neglect it. You select the CV, the MV, and the DV, where the rules must be one CV and one MV, and you can have more than one disturbance. For example, in this case, the CV is H, the MV is F3. The disturbance you have two, F1 and F2. So by completing this pairing CV and V, you can draw the configuration control loop where you start from LT, LC, and the valve. Any question? So, if there
Doctor,
is, yeah.
Doctor,
Yes,
Q
please.
is manipulated valve variable or disturbance variable?
Q.
Yeah.
Okay. For this part, it does not involve yet because this one is for the overall mass balance only. If based on the equation, you cannot see any Q here, right? So this means it's not manipulated and it is not disturbance variable for maintaining the level. So for now, I already complete the level. So for the exercise, we have two remaining balance. The composition or the component balance. and the energy balance. So based on these two balance, I need you to find what is the manipulated and disturbance variable. So you need to complete the following table. So here XA as your control variable. XA, and then the lastly will be your temperature T. So for this part, for your exercise, determine what is the manipulated for XA and disturbance for XA. And lastly, the temperature based on the component and energy balance equation. Once you complete this one, then you need to draw the configuration control loop for both SA and T. So that is the exercise for you to complete it, and we can discuss it on next Monday. If you already complete the exercise, you are free to send the exercise to me through my WhatsApp number, and I will check it for you. So any other question? So it's already 1:50. I think that's all for today. I will share the notes later on. You can refer to my notes and do the revision. If you have or you encounter some of the questions, feel free to WhatsApp me. So with that, thank you very much for your kind attention and have a nice day. Class is dismissed. Thank you.
Thank you,
Thank you,
Doctor.
Have a good day,
Thank you,
sir.
doctor.
Bye, Doctor.
Thank you, doctor.
Thank you, doctor.